live session will be beneficial for the students who are preparing for competitive exam, JEE Mains, NEET, and AB level, GCSE, SAT, and throughout the world, wherever you are. If you are preparing an exam, competitive exam based over this after 12 and pre-college entrance, it will be beneficial for. I'm just discussing how to solve questions based over this. If you have any question, whatever you want to study, whatever you want to read in this class, will tell me and I will discuss that. Is there anyone? Okay, they will grow at once. Yes. Let's see. Let's see. Key points to solve problems of moving charge and magnetic field. Mainly two types of problems. Magnetic force to find magnetic force and to find the magnetic field.
Two people have connected.
Yes. To find the magnetic force.
Give a headline to the topic.
Yeah, I'm giving headline. Yes. This is the topic, right? To find magnetic force and to find the magnetic field. What happened?
Two people came, it became zero. Now it's 1.
Okay. See, in this section, the moving charge and magnetic field, which is just subject of class 12, topic of class 12, of each and every board throughout the world, and it has questions in competition, entrance exam, pre-college entrance exam, everywhere, in India, IIT JAM, Mains, Advanced, and other exams. In foreign, there were another exam, GCSE, SAT, A level, all these things. So this chapter, this topic, this lecture covers that section. See here. How to solve the problems. There are two main sections of problem in this section. In one case, you have to find magnetic field. And in other, you have to find magnetic force. And in most of the cases, while finding magnetic force, we don't need to find magnetic field. And to find magnetic field, in general cases, we don't need to find magnetic force. Let's see. First, how to solve easy question, then moderate, and then tough level questions. So I'm going to cover this to find magnetic force first. Let's see. Is there anyone? Who is the ID? Okay, see. To find magnetic field, magnetic force, see. As we know, the basic formula for magnetic force is Q V cross B. This is a charge. It has some velocity associated with it in a given magnetic field. Velocity associated with a charge means a charge which is moving can feel magnetic force only if the charge is in rest with respect to observer. For pre-college entrance, you can assign observer. In college, you need to relate all these things with respect to an observer. Here, if a charge is in rest, it doesn't experience any magnetic force. But if the charge is moving, it must feel some magnetic force. V is the velocity of this charge, and this V is the magnetic field into which the charge is moving, the charge is flowing. Remember one thing, here is the cross product. This is also a vector, this is also a vector. In very simple case, you normally multiply Q, velocity, and magnetic field, magnitude of magnetic field. Then you get the answer, the force. But here, these two are vectors, and the cross product will decide the resultant magnetic force. And for that, we have to take care of this.
There are zero viewers.
This sine phi. Understood? This is the angle between velocity and magnetic field. Where this is the angle between velocity vector and magnetic field. Means
Somebody is coming and going.
if the charge is moving by velocity v in a given magnetic field, then angle between their direction to the direction of velocity and to the magnetic field, that is this angle. We need this angle to find force. See here. At sine phi is equals to 0 means at phi is equals to 0, sine phi is equals to 0. In that case, you will feel magnetic force as 0. Again, at phi is equals to 180 degree, sine phi is equals to again 0, and therefore magnetic force is 0 again. At 90 degree, phi is equals to 90 degree, and sine phi is equals to 1. In that case, your magnetic force, the charge which is moving at velocity v in the magnetic field, sorry, it hasn't 0, it's the maximum QVB. This is the max value of force, means max force. Is there anyone? Again 0, fluctuating.
Anyone they can hear, don't talk it.
Okay, don't worry about that.
Yeah, it's visible.
Okay. I need to shift it towards this. QVV, this is the max value of magnetic force experienced by this charge. For the same charge with the same velocity in the same magnetic field, due to their angle, due to the interaction, force differs when phi is equals to 0. What is the meaning of this? If your magnetic field is given in one direction, suppose your magnetic field is towards down, this is the direction of magnetic field, and if the charge is moving in this direction, okay, the charge is moving in this direction, in that case the angle between the magnetic field and charges, see this green marker, green pen is showing the direction of magnetic field. Magnetic field is toward this, and this is the direction of charge, the movement of charge, the velocity is in this direction. What will be the angle between them? They are at 90 degree. In this case, if a charge is moving with the same velocity in the same magnetic field but at 90 degree to it, it experiences the force, that is Fb is equals to QVV, because sine phi is equals to 1. In that case, phi is equals to 90 degree. Means the charge is experiencing the maximum force, maximum magnetic force. Now in the same field, this is my magnetic field. The magnitude is also same. Direction is also same. This is the charge, the velocity of charge. As the charge is moving the same velocity, but this time it has different direction. It is following along the field. See, this time magnetic field and the movement of charge, the velocity of charge is also along the same direction. What will be the angle between them? This time the angle is phi, 0 degree. This is the case. When your angle is 0 degree, sine phi is equals to 0, and the magnetic force felt by the charge, this time the charge is moving with the same velocity in the same magnetic field but with a different angle, 0 degree, is 0 this time. Means the charge is experiencing no force, means it has no disturbance. Its velocity is as usual in the direction. In another case, see, this was our magnetic field in this direction. This is the movement of charge, the velocity of charge. This time the charge is moving in this direction. See, what is the difference? In previous case, field was in this direction, the charge was also moving in this direction, and that was phi is equals to 0 degree. This time field is in this direction and the charge is in this direction. The charge is moving in this direction with velocity v. This time magnitude is same, but the angle is 180 degree this time. This time they are making an angle of 180 degree. Phi is equals to 180 degree and sine phi is equals to 0. Again the charge is feeling no force. Means the charge which is moving with the velocity v is feeling no force in that direction. What does this mean? No force. See, the result. What is the physical significance of no force? Means like this. This is the direction of magnetic field, and if the charge is moving in this direction, angle is 0, means there will be no force over this. So it has no deflection. It will travel as usual. If it is like this at 180 degree, in that case it will move undeflected again, no force. But if it is in this direction, this is the direction of field, this is the direction of movement of the charge, the velocity is in this direction, the charge is moving in this direction, it will feel the max force. Means it will either deflect in this direction or in this direction, again through here, anywhere at 90 degree. It will feel a deflection, a very strong deflection by magnetic field with the help of magnetic force, and its path will divert. Now in which direction it will go will decide by cross product. One.
10.0 to 1 C3.
Okay. Start this. It's too slow. If you have any question, then you can tell me. See, you can ask me what you need to know in this chapter. See this. Clear? How will you find the direction of magnetic force by this? See. Remember this right hand thumb rule. With the right hand. With your right hand, do it with your right hand. Right hand thumb rule. See, the forefinger is telling you the direction of charge. Means the velocity of charge is along this direction, and the magnetic field is along this direction. Means this index finger is showing the direction of magnetic field, and then the thumb is showing the direction of magnetic force. Means if a charge is moving in this direction and the magnetic field is towards downward, then it feels a magnetic force in this direction, and the charge is moving in this direction will feel a magnetic force and it will deflect in this direction. Understood clearly? Due to the cross product, we can find the first vector is velocity, put it on the forefinger. Second vector is magnetic field, put it on index finger. And then these two will decide the direction of the magnetic force. That will be the third vector, long thumb. I'm giving an example. See, magnetic field is downward, means downward toward this, the magnetic field, downward towards the flow. And the charge is moving in this direction. Okay, the charge is moving in this direction. Let's see. See this. Is it visible? Charge is moving in this direction. Magnetic field is downward. The force will be in this direction. Means the charge which is moving in this direction will get a deflection in this direction. Understood? In this direction. Similarly, if magnetic field is downward and the charge is also moving downward, it will feel no force because it has same angle 0. If the magnetic field is downward and charge is moving upward with an angle phi equals to 180 degree, in this case it will also feel no force. Means there will be no deflection. You can use any other angle. Suppose at 30 degrees. See. Let it grow the numbers. See, this is for easier question. Now we are growing the level and you will get some moderate level questions over this concept. Let's see now. See, now we get some moderate level question over this concept. See. See. This is the magnetic field. Understood? The magnetic field is into the plane. Means the magnetic field is into the plane. This is the direction of magnetic field. Now a charge is entering here by velocity v. This charge is entering in the magnetic field by velocity v. Means, see, this is a magnetic field. How much fear? 0. See, this is the direction of magnetic field and the charge is entering like this. What will be the angle? The angle will be 90 degree in between them. Means you have to take pi as 90 degree. As it enters in the magnetic field, it will feel some force due to the magnetic field. That is the magnetic force. See here. Magnetic force over the Q. This is the magnetic field. In B is equals to QVB sine phi. Because angle is 90 degree this time. And QVB this. Understood? If it enters at any other angle, not 90 degree, 60 degree, then simply you have to put here 60 and put the value of sine 60 as root 3 by 2. But in this case, there is no 60 degree. It is entering at an angle 90 degree here. And we are using phi as 90 degree. And sine 90 is 1. So this is the max force. Clear? And as we know, if a charge is moving, if something is moving at velocity v, and the direction of this force, remember one thing, as we know, the magnetic force is the cross product of velocity vector and the magnetic field vector, and the cross product is always in the third plane. Remember one thing, as I'm showing you again, see this. This is magnetic field, this is the direction of charge movement, means velocity v. If this and this, if they are, this is magnetic field, this is this, whatever be the angle, let me show you, this is a cross product. On the cross product, I'll make another video. See this, then the direction of magnetic force will be in this direction, means force is along this, force will be along this. And remember one thing, this formula works on positive charge. When your charge is positive, means positive charge. If your charge is positive, in that case this works, and this will show you the direction of force. If your charge is negative, in that case you have to switch it. Find force of a positive charge with the same magnitude and then inverted direction. For negative charge, you have to find the force on the positive charge of same magnitude and then reverse the direction. If this is the magnetic field and this is the direction of charge, positive charge, so this positive charge is feeling force in this direction, then if it was a negative charge, in this case it will feel force in this direction. Just find force for positive charge and invert it. Inverse it. So here, and due to extension of this code, anyone here? Who's there? What happened?
No,
Okay.
it tilted and the camera angle.
See.
Good. Exactly about it. So the question.
This is a concept. This F equals to QVB. It's entering at an angle 90 degree. And as it enters here, the charge is feeling a force, magnetic force in this direction. The charge is feeling a magnetic force in this direction, along perpendicular to its motion. And you know that perpendicular vector, perpendicular force can't do any work. It just changes its direction. And earlier it was moving like this. Due to the presence of this magnetic force, it will go in a circle. Each and every point, the magnetic force is acting in this way. Clear? And due to this magnetic force, it will go in a circular track. If there is no field here, it will come out in a circular track. And that's why, so FB is equals to FC. FC is centripetal force. This is centripetal force. The charge is moving in a circular motion. That's why it feels some centripetal force. And the force which is doing the job of centripetal force here, that is a magnetic force. See, QVV is equals to mv squared by r. R is the whatever circular track it has, the r will be the radius of that track. V cancel, r equals to mv by qv. Here r is the radius of the track, and v is the speed, q charge, v everything you know. R equals to mb by qb. This is very straightforward concept. Means the easier problem based upon magnetic force will be like this. You have to find radius of a track when a charge is entering in a magnetic field. mb by qb means R is inversely proportional to V, and due to this and directly proportional to velocity and mass and charges. So the graph will be like this. R, B, this will be the graph. Clear? Now see, once we know the radius and the velocity, you can ask that if I'm increasing the magnetic field in this region, then what would happen? Then it will go in a circle, perfect circle. And then we need, see, if it will go in a perfect circle, then you can ask for the time period. Time period. What will be its time period with this velocity under this magnetic force to cover one revolution of this circular track? And this is 2 pi r by v. Put the value of r from here, we get 2 pi m by qv. So time period is also inversely proportional to the v, magnetic field. In that case, we have again the same type of graph here, T and B. Clear? Time period is also inversely proportional to B. See, after time period, someone can ask you, what will be the frequency? Is there anyone? 0.
There is one viewer who is.
What happened? Live is not getting successful this time.
There is one person who is coming.
Let's see. 2 pi m by qb, Tb. And now the frequency.
Why fill up a part?
Yes.
The
Let's see. See, what will be the frequency? Frequency is 1 by time period, and that is qv by 2 pi m. qv by 2 pi m. Understood? What does it mean? The frequency means if the charge is going in a circular track under the influence of magnetic force, then it has a radius this, and the time taken to cover one revolution is this, and the frequency, what is meant by frequency? Frequency means, suppose you have gone to jogging in a park and you are running at the circumference of the park. If you're taking 10 minutes to cover one revolution, it means that is your time period. If you're taking 10 minutes to cover one revolution, that's your time period. But if the distance covered by you at the circumference in a second is your frequency. Understood? That's the difference. But here, see, frequency is directly proportional to V. F is proportional to V, and the graph is here, this. Notice the differences in the graph of time period versus V, radius versus magnetic field, frequency versus magnetic field. Understood? You can get the questions which are easier over the force, magnetic force, in this way, on these concepts. Now, growing the level, increase the level of this section. This time you are getting some slight tough questions. Let's see how it will go. How it will be.
You know what? The whole more than TV.
See, just single. I think yes, some of our students coming and going. See. Slight tougher questions now, this time. Take this section. See. In a given particular region, there is some magnetic field. And in all these questions, your field is constant. It's not increasing or decreasing. It's constant, fixed value. The value of magnetic field is fixed throughout the region. And in time also. Throughout time also. See. See here, this is the magnetic field in this region and it's constant. It's like this. Clear? Magnetic field is into the plane. V is used to represent magnetic field into the plane. Direction of magnetic field is in this. Notice. A charge is entering from here. With velocity v, the charge is entering in this magnetic field with velocity v. And remember, the length of this region is L. And this charge feels force as it enters. It feels a force in this direction, magnetic force, and that magnetic force turns its direction. The charge was moving in this way. Due to the effects of magnetic force in vertical direction or in normal to it, it will get a deflection. And when it reaches here, outside this region, there is no magnetic field. And that's why in whatever direction it reaches here, it will go undeflected after. So your problem will be to find this distance, this vertical distance within which it feels magnetic force. It was going like this, and till the end of the region, it goes like this, and then it has in this direction movement. So its deflection from its original path is this d. You have to find the value of d. You have to find the value of d. Let's see. I told you that this is slight tougher question this time. You can't solve it directly by formula. You have to understand the nature of the question. See here, what's the nature? First of all, think that it's a two-dimensional question. Earlier it was moving in this direction. Due to the effect of force, it goes vertical. It has deflection in vertical direction. Means for something you have to work on x-axis, and for other thing you have to work on y-axis. So remember motion in a plane. Combination of motion in a plane with vector in magnetic field. There are three concepts in this question. One is the first is magnetic field, feels magnetic force. Second is vector, and third is motion in a plane. Remember one thing. I'm taking this as x and this as y. This is x and this is y. Let's see. Velocity along x-axis. What do you have along x-axis? V is along x-axis. L is along x-axis. Now see, your force along y-axis. Along y-axis, we have force. The magnetic force is along this axis. Y-axis, clear? And the deflection from the horizontal motion, deflection from horizontal motion in vertical direction, D, that we have to find. D is along y-axis, remember, understood? Now, solve for something along x-axis and solve for some other thing on y-axis. See here. As we know, if there is no force in x-axis, there is no force in this direction, right? There will be no acceleration in this direction. Then value of acceleration is 0 here. And the force is along y-axis, so value of acceleration is something here. This force by mass. Magnetic force by mass. Clear? But here. And I'm telling you one thing, time. Time is not a vector, neither scalar. It's beyond the scope of this, beyond the scope of this course and beyond the scope of this book. So think time has no component in any direction. Time is universal for classical mechanics. Whatever time it takes from here to here, if it has force in this direction, it will take same time from here to here. Means if it's traveling along this, then whatever time it takes to go here, in the same time, horizontally it travels up to here and vertically it travels up to here. So time is same in both the directions, both the axes, not direction.
Getting some questions.
Yes. What is the question?
Someone is. Are you a student? It looks like someone came a wrong channel.
Okay, don't worry.
Yeah. Okay, teach it.
And words? I will do cardio exercise, everything, don't worry. See here. Acceleration along y-axis, vertical direction, is Fb by m, understood? And acceleration along x-axis is 0, clear? So there is no component of time. Time is universal for both the direction. So what can we do first? From this data, we calculate the time from x-axis, whatever given along x-axis, that is L by V. This is the time it takes from here to here. Within same time, it will travel from here to here, means it reaches from here to here. Now, AY, that is FB by M.
Okay, the person who is commenting on this live,
Yeah.
if you are a student, then you can try to understand what I am teaching, and if you are not getting, then
don't worry.
you are not forced to view this video. But please make the comments respective.
Oh, don't worry. Let it see this. See, if you have any question, then ask me. AY equals to FB by
If you
M.
want to understand, and if you have any problem that you are not able to solve,
AY
then you
equals
can
to
ask.
FB by M. Understood? And what is the magnetic force it's feeling here? It is feeling a force QV cross B. And as it's entering, see, magnetic field is into this, charge is along this. So angle is 90 degree. As it's entered here, we have 90 degree as an angle. Sine 90, and sine 90 is 1. So our acceleration will be QVB by M. Clear? QVV by M. Thanks for increasing my view. Don't worry, just watch. QVV by M. Clear? 0. QVV by M. See, AY. You need to find vertical deflection, and it's along y-axis. You have acceleration for this direction and time. You do not have initial velocity along this direction. So D equals to half AYT square. That is half for AY, put QVV by M, and T square L square by V square. That's the value of vertical deflection. This, how much it will deflect from its horizontal path to vertical. This will be the question that will be tough than the earlier one. Understood? I'm going to analyze one more problem which is also slightly tougher than this. Clear? For such questions, understand the nature. Try to understand the nature of question. Figure out how many concepts are hidden. As this question belongs to the chapter magnetic field and from the section of magnetic force. So you have to find magnetic force. Clear? You have to find magnetic force. So one concept is here, magnetic force in magnetic field. Second, as these are vectors, we need vector addition, or we need vector analysis, we need vector calculation. And the third one is it was going in this direction due to some force, it has deflection. This means motion along two dimensions. One is along X, another is Y. So three concepts, one is direct, visible, and two are hidden. You have to find out this concept to solve a tough question. Only then you will solve it. Otherwise, you'll get trapped into the question. The visible concept is magnetic force in magnetic field. And the hidden concepts are use of vector product and motion in a plane. Understood? See, now another problem. How long it has been?
It's past 43 or 44.
43, yes. Who is in the line? Oh, don't worry. Increase my view. It's healthy for me. See this. Listen, see here. Another type of question based upon force. It's also a tougher question. Tough question, not tougher, but tough question. See, the reason is filled with magnetic field, constant magnetic field, not changing magnetic field, neither in magnitude, neither in time. See. This means cross means field is into the plane. If I write like this, it means that field is out of the plane. Just switching on the direction, nothing else. See here. If a charge is entering in this at 90 degree, I already discussed the concept, but now I'm going to explain this. This time the charge is not entering at 90 degree. It is entering at some other angle. Let's see. Like this. I'm showing you, I'm drawing this field like this here. The same field is like this here. To make it easy to understand. Now see, as a charge is entering at 90 degree. This is not my case here. My case is something different. Let the charge is entering at an angle theta. Not 90 degree, neither 0. What would happen? Does it go in a circle again like that? No, it will not go in a circle. It will go in a different type of a structure. It's something like spiral. See here. As the charge enters in the field, this given field region with velocity v, but has an angle theta. Notice v is vector. It has two components here. One is along this, and another will be along this. Clear? Velocity of the charge has two components. One is along this, other is along this, and field is along this. Now, V has two components. That is V cos theta perpendicular to the direction of field and V sin theta parallel to the direction of magnetic field. Clear? V has two components, V cos theta and V sin theta. V cos theta is perpendicular to V and V sin theta is parallel to V. Now, if a charge enters in a magnetic field at angle 90 degree, it goes in a circle. So this component, which is perpendicular to V, drives that charge in a circle. Clear? And due to the formula, we can solve it by getting V cos theta drives the charge in a circle in B. Then apply the formula to find the radius. mv squared. This time your v is v cos theta, not whole v, only the component. V cos theta squared by r is equals to q v cos theta b. Clear? This is the velocity through which the charge is moving perpendicular to v, this component. And what will be the r? mv cos theta by, oh sorry, I have done some mistake. See, what a silly mistake it is. As it is moving with v in this field at an angle theta to the vertical, then this will be cos theta. Component which is adjacent to angle is cos theta, and this will be sin theta. This is sin theta. Clear? And inverse is also here. V sin theta is perpendicular to V, and V cos theta is parallel to V. And here V sin theta, again here V sin theta, V sin theta by QV. Remember, this time your velocity is this. Your radius is this. Radius of this, when charge enters at an angle theta to the magnetic field, it has two components of its velocity. One is V sin theta. This component is perpendicular to V, and V cos theta, this component is parallel to V. And this component of velocity drives the charge in a circle, and through that the radius of the circle is this. Clear? This is the radius of the circle, means the charge will go in a circle, but it has some radius. The radius is this. Now what will this component do? What will this component do? This component will drive it down. See, earlier, now find the time period. If the charge is in a circle due to this component of velocity of radius this, what will be its time period? So 2 pi m 2 pi r by v, and this time your v is sine theta, and 2 pi, put the value of r here, v sine theta qv. Notice v sine theta cancel, and again our time period is 2 pi m by qv. Remember, time period is unchanged. Radius got changed, time period is unchanged. 2 pi m by qv. And if time period is unchanged, then frequency is also unchanged. Clear? Frequency is also unchanged. So your radius is this, and the charge is going in a circle due to this component of velocity of radius this. In a circle of radius this due to this component of velocity. That circle will be, but remember here, there's another component of velocity is acting here, and the time period it takes to cover one revolution is this. So this component of velocity drives it downward within that time period. Then it means we don't have, suppose the charge is entering in this region. See, I'm erasing this. Suppose, see, again drawing the same figure here. This is a field, and the charge is entering here. The charge is entering, it has components of velocity here and here. It will go in a circle due to this component of velocity and circle of radius, and in this time period, it takes the same time to come to the point. Time period is, but this component is still there. It walks, and it will drive it downward. It drives it downward. And what would happen? It will never not go in a circle to the same, it will not go in a circle, it will become a spiral. The time it takes to cover one circle, during that time, the component this v cos theta drives it down, and it comes here. Again, as it goes in a circle of radius this, in this time period, the v cos theta drives it down. And so we'll have a spiral. This time we have a spiral path. If charge enters with an angle in a magnetic field, it will not go in a circle, it will go in a spiral. Clear? It will go in a spiral. And the radius is determined by v sine theta. This is your radius of the loop of a spiral, but the pitch, this gap between two consecutive loops of a spiral is called pitch. The gap, this pitch, is determined by this component. So pitch is equals to, remember, pitch is the distance traveled by charge due to this component, and that is in the time period, that is v cos theta and capital T. So pitch will be, see, I'm writing pitch is equals to v cos theta into the time period. Let me erase some part. See here, I'm erasing some of here. This is not to see this. Here, pitch is equals to v cos theta and t. And v cos theta is v cos theta, and your time will be 2 pi m by qv. Clear? 2 pi m by qv. This is your pitch, means the shift in the consecutive circular loop to form a spiral is this, that is pitch. Clear? This is slight tough question. And what will be the time?
It's around 1 hour.
Is it 1 hour?
Yes.
Oh. See, 1 hour. Where is the time? There's no time. 55 till so. Let me explain. If you want to make it slightly harder question, see here. Within the same question, I'll do only qualitative analysis of that question, not the quantitative analysis, because the quantitative analysis is quite linear in any other class. As you want, message me for the class, I will do that. See. Quantitative analysis. If we take magnetic field different than this, not uniform and constant, if our magnetic field will be suppose, see, the spiral changes its shapes. It will go like this, in this tornado style. See, that spiral look like this. The trajectory of charge changes from the uniform spiral to this type of spiral, and this like this. When? Do you know when it happened? When does it happen? It will happen when the field, see, R is inversely proportional to magnetic field. If R is bigger here and gradually decreasing towards the center and then again increasing, means that field is less from here to here. Field is very high. And again field is less. Clear? So from top and bottom field is less, decreasing, and at the midfield is very high. That's why R is less, and here its spiral is bigger. The loop of spiral is bigger here, and here is smaller. See this. See, this is magnetic bottle. We call it magnetic bottle. What does it mean? See, here radius is small, means field is very high. Field is high and slightly gradually decreasing towards the center, means from here field is less, and again gradually increasing to the bottom end, field is high. Understood? This is magnetic bottle, and this is the concave spiral like this. So these are the pictorial diagrams. Only qualitative analysis. For quantitative analysis, you need some extra theoretical concept. Here you have checked field is non-uniform, and here field is diverging at the center and converging at the ends. Radius is converging and it's diverging at the center. V is high at the ends, V is less at the center. Here radius is diverging at the ends and converging at the center, means B is less at the ends and high at the center. So that's for, you can get all the questions, not all, but most type of questions based on the force, calculation of force. In next class, if you demand, then I will deliver. In next class, I will discuss the calculation of magnetic field. From this chapter, these are two major sections of questions in pre-college entrance exams everywhere in the world. Oh, thanks for watching. Thanks for being in my life. Thanks for watching.
Indeed.
No one is here.
Wait. Cross it.